Swayam Prabha. Digital India. Educated India.
Welcome to NPTEL Phase 2 lectures on the course titled Mass Transfer 2. Myself Nishit Verma, I am the professor at IIT Kanpur, and in this course we will have 40 odd lectures, right? Each lecture lasting around 1 hour. So before we begin this lecture one, let's go through some of the administrative procedures. Okay, so as we said, there will be 40 lectures and we will like to divide into several sections. Okay, now this is third year undergraduate level course, so which means it is expected that we have some exposure to other chemical engineering courses, at least at the second year levels. For example, fluid mechanics, some course on heat transfer, all right, some course on stoichiometries, process calculations. So of course we begin this course again with some introduction to mass transfer, certain basic and fundamentals. What we do right now, let's note down books, textbooks for this course. All right, so let's note down certain points here. So this is the course on mass transfer 2. Okay, and here essentially we will follow textbooks. So let's make a note of these books. One is, you may be familiar with this, Mass Transfer Operations. The author is R.E. Treball. All right, it's a very popular book in chemical engineering. It's a McGraw-Hill publication. Third edition should be available. 1980. So we will have most of the lectures covered from this textbook. All right. There is another very good book by the Indian author Datta here, B.K. Datta. This book is also available Prentice Hall of India. So what we will do, most of the theoretical aspects we will cover from this book by Treball, and some of the numerical examples we will deal with from this book, separation processes. All right. So the second book by Datta, it has different levels of examples, so we will choose few of them from there. There is another book by Wankat. All right, so let's make a note of these two textbooks as well. So these books are essentially for reference purpose. So the title is Principles of Mass Transfer and Separation Processes. All right, so the author here is B.K. Datta, and this book is published by Prentice Hall, India, 2007. There is another very good book titled Equilibrium Staged Separations, and the author is Philip Wankat. All right, this book is also from Prentice Hall, 1993. So all these three books should be available in your book stall. You can order the books, right? As we said, let's note down the prerequisites for this course. So this is a third year level course. That means you should have elementary knowledge of fluid flow. I'm sure most of the university they have at least one course at the second year level on fluid flow. Heat transfer also maybe second year level, or at least at the third year level. In chemical engineering, this is the first course on stoichiometry in most of the university, or chemical engineering calculations. So actually this is a third year level course, alright, and what we do in this course is separations, alright. So you may have done, when you have taken the course on separation, on calculation, process calculation or stoichiometries, you must have done some calculations on, say, combustion, distillation or absorptions. So the orientation of this course is to deal with certain unit operations. Okay, so what are the unit operations? We have, say, certain phase, a liquid or gas phase containing, say, at least binary components A and B, and we have been asked to separate A from B, or in other words, we have been asked to deliver a product containing most of A's. So the purity is, specification for the purity is 99.99% of A. Other phase rich in B. Alright, so we have two phases, A and B. So there is a separation. There is one component which is rich in one phase, other component is rich in the second phase. So how do we achieve it? We have set of unit operations. Alright. In some cases, maybe we just have one unit operations. So what are these unit operations? These are the methods, right? So essentially you have some equipment by which you can accomplish, you can achieve these separations. For example, distillations, absorption, adsorption, drying, extractions. So these are the several unit operations in chemical engineering. For this course, we have listed certain unit. We also have, we said in the beginning, we'll have few lectures on introductions to basic and fundamentals. So we will have elementary introduction to this diffusion fixed first law, alright, so that we can set up the basic and the fundamental equations which is required, in solving certain class of problems. Okay, so let's note down again the objectives here in this course. So the main objective is we want to address, we will begin with fundamental concepts. Alright, so when we say fundamental concepts here, we will be essentially dealing with diffusion, molecular diffusion. Okay, and then we will switch, or we will start certain unit operations, UOP. Okay, so what are the unit operations which are listed in this course is absorption. So we will begin with absorption. So this is the way this course is divided, starting with absorption, distillation, we have extraction, adsorption and drying. Alright, so of course we will begin with the diffusion, and then you will see that you may have come across the parameters like mass transfer coefficient. So we will have certain theories here which will tell us how to calculate these quantities like mass transfer coefficients here. Alright, so before we begin take these topics here, absorption, distillation or different unit operations, let's try to understand what we do here. So let's say we have a feed. Okay, so when we say feed, this is our starting material. Now this could be liquid, alright, or this could be, say, gas, or we can have even the solid phase. Okay, this contains, let's say, at least two components, A and B, and we have been asked to separate B from A. That means when we say separations, practically we do not have 100% separations. That means what we are expecting here, that we will have two phases. Alright, most commonly both phases contain A plus B. However, in one phase A will be larger and the other phase B will be larger. Okay, so we say that this is, let's say, phase 1 and this is phase 2. So in phase 1 A is rich, it's richer than B, so it has certain purity. Let's say we say that 99.9%. other components, it's rich with B. So A is lean here. A is lean. It's rich in B. And the composition here, this could also be 99.9%. All right. So this is the way we are separating it. We have two phases. In one, A is very large quantities. That's our desired product. But B will appear as an impurity. We won't be able to have 100% separations. In other components, other phase, we have the second component B, which is rich, like 99.9%, and A will appear as an impurities. Now, how do we achieve this? Going from the left, a phase, liquid or gas or solid containing A plus B, two different phases, two different streams in which A is larger and the second B is larger. We accomplish it through UOP, unit operations. All right. So the schematics of this unit operations, now there's not like one unique geometry here. We have different type of unit operations. So let's say we have absorptions. All right. So absorption is one of the unit operations. It's also a process. So when we say unit operations, we are saying that these are different processes. So let's give an example here, that we have a gas phase, let's say air. Okay, so air, it's in gas phase. It contains, nitrogen, oxygen, other species. Let's say by and large we say this N2 or oxygen, and the other species, so this let's call it as A. So when we say A, it's a mixture of nitrogen and air, bulk quantities. And the next B, which we want to separate, let's say it's a sulfur dioxide, which is very small quantity in atmosphere. Let's say maximum it's 1%. All right. So what we're trying to say here, that this air which comes out from, say, power plant, all right, it contains some amount of sulfur dioxide. So you're aware of this air pollution's environmental aspects. Air, if it contains 1% of sulfur dioxide, this has to be treated. Okay, one has to remove the sulfur dioxide from the air stream before we throw into atmosphere. So it's a there is some environmental regulations. It's an air pollutant. So what we do, how do we achieve? We bring in contact with water. Water is a very good solvent. You can also bring in contact with caustic, sodium hydroxide, KOH, etc. All right. So now we are looking at the unit operations, or the method or the process, which is absorption. So what we do in absorption, we have this distillation column, absorption column, which is packed here. So we'll talk about this, we'll come back to this at a later class. So we have essentially packed bed. So there are certain packings inside. These packings, what do? They improve contact between air, which we want to treat, with water, or let's say put general solvent. So now we are talking of two phases. One phase is gas phase here, which contains A for air, nitrogen plus oxygen, plus the second component B, which is sulfur dioxide. We want to treat with solvent, so it's a different phase. So it's an aqueous phase, or maybe it's a liquid phase. Now it's a phase 2. All right, so this is a phase 2. This is phase 1, and this also contains, say, component water. This water could be pure, but very often this water is also contaminated with certain amount of B, which is a very, very small quantity. So in other words, this is 1%, is possible that this B may be 0.001%, or let's say water is pure. So what we are doing here, we are bringing two phase in contact through this packing. So there will be, if you look at just one packing, so this is some kind of solid materials, water will trickle past this, and air or sulfur dioxide will diffuse into this. So it's going to be solubilized here. So what we do now, we have air, which is treated air here. So it's an effluent. So let's call it influent, and this is effluent here. But this effluent now contains air in which sulfur dioxide is very small quantities. So even here we have A plus B, but this B is a very small quantity. All right. So now look at what happens to this water solvent. Now when solvent flows past this absorption column, it picks up sulfur dioxide, which means now this water will also contain B the way it was here, but now B will be larger quantities. So what we have done by absorptions, it's an unit operation, it's a method, it's a separation by which we have separated or we have removed sulfur dioxide from one phase, which is air here, by bringing another phase, which is water here, or aqueous phase or some other liquid, and we have carried out these separations. Now look at both the streams, air after treatment and water after treatment. Air after treatment also contains A plus B, air and sulfur dioxide, and water after treatment contains water as well as B, but this B is very small quantity, large in air. So when the air is coming out from the absorption column, it's lean in sulfur dioxide, but water or the spent liquor contains very large amount of sulfur dioxide. It's highly concentrated. So we have been able to achieve these separations by absorptions. So there is a mechanism. Sulfur dioxide has a large solubility in water or certain solvent. Okay, you can choose. So if instead of sulfur dioxide, if you have carbon dioxide, then you have different type of solvent. Okay, so now let's look at different unit operations like distillation. Right. So distillation, also known as fractionation. Okay, so what here we want to achieve? Let's say again start with air. We said air contains oxygen plus nitrogen. So what do we do now? This air can be liquefied. So you have some heat exchangers here. Now this heat exchanger is beyond this, you may be in different unit operations, a different course you have dealt with this heat exchangers. For our purpose, this air, which is gas phase here, it's liquefied. So same air is now in the liquid phase. You bring to a column, you may have seen it, or you may have seen in the textbook at least, the distillation column. So it's a different unit operations. It has a different arrangement here. So there we talked of continuous packed bed. So we have this tall column, and it was packed continuously with certain solids. So it's one type of unit operations. Here we have different situations, different configurations. These are the trays. Okay, again we'll come back to this in the later class. For the time being, what we're trying to say here, that now this air is brought in here. So there is a heat exchangers, all right, and then by distillations, it's possible to have the top quantities, all right, and the bottom quantities. So two phases here. This is also maybe after condenser. This is the liquid phase, but this liquid phase will contain both oxygen plus nitrogen, but nitrogen will be much larger here than oxygen. Similarly, at the bottom you will have some heat exchangers, arrangements like this. We also have a bottom product which is also liquid, all right, and this will also contain oxygen plus nitrogen, but it's possible here that this oxygen is rich here. So we are talking of again separations. We want to separate oxygen from nitrogen. We are producing nitrogen in which oxygen is an impurity. So here if oxygen is, let's say, in atmosphere 21% and nitrogen is 79%, it's possible to achieve a much larger purity for nitrogen. So we say that, well, nitrogen here is 99%, oxygen is 1%. On the other hand, here oxygen is 99% and nitrogen is 1%. So look at the similarity between this unit operation distillation and absorptions. Here we start with air, gas phase. Of course we liquefy, it's a liquid phase, contains A plus B, and we separate in two streams. Both are liquid phase. Maybe from the top we have the vapor, which again we have liquefied into liquid phase. So there also we have two different phases. Top phase all contains A plus B, but is rich in A. Bottom phase contains A plus B, but is rich in B. So that's a separation. What is the mechanism? In case of absorption, we had solubility, right? One solvent contains has strong affinity for one type of species. Here, what is the mechanism? This mechanism we will deal with later. It depends upon relative volatility. You'll have to apply Rawls' law. So one component is more volatile than the other component, so it appears more in the top stream. The one which is less volatile appears in this bottom product. So from the perspective of chemical engineering point of view, both are unit operations. Both have achieved the separations. The idea is to separate A from B. Here we add energy or we take away energy to achieve the separation. In case of absorption, we add a third component. We are adding a solvent to separate A from B. So there is a similarity in the two unit operations. There is a difference in the unit operations. Now there is another important thing to note here before we give another example of unit operations. Most of these unit operations may involve reactions, chemical reactions. Most of the unit operations may be non-isothermal, right? It's possible, which means there could be production of heat, or there could be heat loss there, right? Reaction could be endothermic. For this course, this reaction part of it, we assume that reaction is negligible, or it's not considered in our case. So you have different course on chemical reaction engineering where you deal extensively with the reaction part of it. So we have one very exclusively mass transfer. Okay, why I'm telling this? Because in distillation it's possible to have a reactive distillations. So that's a different type of unit operations where maybe you have a combination of distillation and the reaction. Okay, or you can have extractive distillations. So you bring another unit operations. Okay, so now talking of this heat transfer aspect of it, your certain separation process, it's possible, could be exothermic, could be endothermic. Say absorptions, it's possible that when sulfur dioxide is absorbed in water, there could be production of heat. So the reaction could be non-isothermal. Again, for most of the unit operations, you will see that our discussion or analysis will be isothermal, assuming that process is isothermal, or we are neglecting heat transfer aspect of it, except this distillations, where you will see that there will be different method where we have very comprehensive energy balance. Okay, there is another unit operation, drying, that will be our last topic there, where you will see that we will have to make extensive energy heat balance. So as we said that whatever unit operations we have very extensive discussion on mass transfer aspect. Wherever required, we will have heat transfer aspect. Okay, so let's continue and let's give another example of say another unit operation here, extraction. So just like we have absorption, distillation, we will have discussion on extractions. Now what is extraction, or sometimes this is called liquid extraction. It's also called solvent recovery, okay, LLE. So what we have here, now let's look at this example. Water, let's say water is contaminated with nicotine. You must have heard of this, it's toxic substance, organic substance here. So water, now it's a liquid phase, it contains very small amount of nicotine, a very small 0.01%, but this nicotine is injurious to the health. So how do we remove nicotine from water? Absorption may not work, distillation may not work, because we may not have appreciable amount of the solubility or relative volatility. So LLE is another unit operations where what you do, you bring this liquid of water plus nicotine with another liquid like kerosene. All right, so now we have a liquid phase and we also bring another liquid phase here, but different species here, kerosene. Now when you mix these two, what you will get, and I will come back to this, you will get two different phases. In other words, in a beaker, if you take a small beaker and water, nicotine, and bring this kerosene, you will see that two phases have appeared. You can see them very clearly. They are all it means they are immiscible. Now both phases, the top and the water, will contain nicotine. So one phase we are saying that water contains nicotine, but it's a very small amount. Another phase, which is kerosene, will also contain nicotine, but nicotine will be a very large amount here. Alright, it's possible that certain kerosene will also appear here and certain water will also appear. That's possible. But what we have done essentially, we have brought down this level of nicotine in this water by bringing another liquid here, kerosene, so that now this water, which contains very small amount of nicotine, that may be acceptable for whatever purpose we have. Okay, so this extraction is also similar to the previous unit operations, distillation and absorptions. Here what we have done, a liquid phase, you bring another liquid phase which is immiscible, so that you have two phases and you transfer one component from one phase to another phase. So water, at the end of this unit operations, you will have two phases. Both phases will contain nicotine, but in one case nicotine is a very small amount which is tolerable, and another phase is highly rich in nicotine. So essentially we have achieved our objective, that we have been able to separate nicotine from water. So this unit operation is extractions. Again, talking of similarity, we have separations. Talking of difference, now we have different mechanism here. What is the mechanism here? Now we are talking of difference in solubility. Solubility of nicotine in water is different from that in kerosene. It's more soluble in kerosene. So kerosene is able to extract nicotine from water. What was the mechanism in distillation? Relative volatility. A component was more volatile in B. What was the mechanism in absorption? A is more soluble in water. Alright, so this is the way we extract sulfur dioxide from air, and the water which spent liquor which we collect contains most of the sulfur dioxide, and air has become thin. So from practical point of view, all these three are unit operations in which we have separations. There is a difference in mechanism. We have different approach to address certain set of problems. Okay, so let us take another example of unit operation, which is adsorption. Notice here, state of absorptions B, we have this adsorption here. So what it is? So let's say again air, gas phase contains, say, contaminants like VOC. You may have heard of this, volatile organic compound. Right. So let's say we have benzene, or we have xylene. So these are example of volatile organic compounds. So air contains, let's say, VOC, very small amount, let's say 0.5%. So it is vapor, toxic compounds, and we want to remove this VOC. So what we do, we bring this stream of air in another packing. So we have this again very similar to absorptions, packed bed column. Now this packing is of charcoal, or let's say carbon. Okay, so what happens here? Now bring in contact with this air here. Okay, and then after some time, what will happen? This charcoal bed or packed bed will become saturated. This packed bed will be now saturated with VOC. So if you start with again this packing, let's say we have this horizontal packing, bring in contact with air, packing of, as we said, some coal, charcoal. We'll talk about different type of adsorbents. It contains certain level of VOCs. So in the beginning, when the charcoal or these adsorbents are fresh, then at the exit you will see that there is no VOCs coming out of this. So you put some instrumentation here, it will not be able to measure VOCs. Why? Because VOCs has been adsorbed. VOC has been adsorbed by this charcoal. After some time you will see that slowly and slowly this concentration will increase at the exit, till this level has reached same as the inlet level. Then one will have to stop it. So what operation is here? we are starting with air, which contains VOC. We bring in contact with the different phase. So this is gas phase. Now we are bringing in contact with the solid phase. Here also we achieve separation. So for long time, or for this time t, till the bed is saturated with VOCs, this we also have two phases. One is treated air, alright. This also contains VOC, but very small amount of VOC. So for a long time, this VOC amount is almost negligible, alright. And the second phase, which is stationary here, is charcoal. Now this charcoal is containing VOC, and this amount of VOC is slowly is increasing till it gets saturated. So this adsorption is also a very important unit operations. It's also used in water decolorization. This is a very old practice, very old application of charcoals, or just like today we have in case of water purifier. So you have continuously water you feed through this purifier. Water contains a lot of dissolved solutes, TDS. It's getting adsorbed in this charcoal or whatever adsorbents you have. So for some time till this adsorbent gets saturated, you have two phases. One is a water phase, but that contains very small amount of TDS, very small amount of fluorides. And the second phase, which is stationary, is a solid phase, which is slowly picking up the second component, whatever you have, fluoride, arsenic, or TDS, or volatile organic compounds. Once that bed is saturated, one has to regenerate this. Okay, so this another unit operations. We'll be spending time on this adsorption here. All right. Then after that, we will spend some time on this drying. So what is the dryer? You must have seen it, even in household. You have, let's say, sands, okay, which contains moisture. So some applications where sands contains moisture. So now we are talking of solid phase sand, okay, which we want to treat. In other words, we want to apply certain unit operation so that this moisture, let's say it contains a very large amount of moisture, let's say 10%. Okay, now we want to apply this unit operations drying. So what we will do now, one has to bring hot air. So look at the difference and the similarity between the different unit operations. Here in the solid phase, we want to treat solid phase. Earlier we wanted to treat, say, water containing VOC. We wanted to clean air from sulfur dioxide. We had again water containing nicotine. All right. Now we have a solid phase sands. It's a moist sand. We want to dry it. That's called dryer here. So now what we will do, we will bring hot air, and then still we will have separation. Hot air, it will pick up moisture. So now this air will contain moisture, very large amount. Slowly this will pick up as air will pass through some bed here. So you can have again a packed bed of sands. Let the air go through this. So moisture will be picked up by this air here. And then whatever sands you have left, you have in this stationary, as a stationary phase, this will also contain moisture. But this moisture amount will slowly decrease till it goes to the level of whatever acceptable, maybe 1%. Then you say that your sands are relatively now drier. Okay. Now again, this unit operations, make a note that now we are bringing this hot air. That means now we have to look at heat transfer. So this is one unit operations where we have both aspects of mass transfer as well as heat transfer. In the previous unit operations, or the example which we had, say absorption, extraction, all right, or adsorptions, they can also be accompanied by certain release of heat or gain of heat, loss of heat. But generally for this course, we are saying that this process is more or less isothermal. That means the amount of heat released plus or minus exothermic or endothermic, it's a negligible. Distillations, if you notice very carefully, we started with air. Okay, we can also have liquid which we have to distill. So whenever we have distillation, there also we have energy, energy considerations or enthalpy considerations. So these are the two unit operations, drying and enthalpy, where you do have very exclusively discussion of heat transfer. Otherwise, the other three unit operations for this course, we will have mostly isothermal process. Okay. So through these examples, what we have tried to say here, that in all these unit operations we have some similarity and we have a difference in the mechanism. Okay. Now what we want to achieve in this course, or what are the other objectives, that this course is about process design. All right. So that means, say if we choose absorptions, what we will do in this in the absorptions, that given the quality of air, how much sulfur dioxide it contains, given the flow rate of air, given the temperature, we will like to address the questions like how much amount of water is required, solvent is required, or how high, what should be the height of the column, or what should be the amount of this packing, what should be the diameter of this. So that's like process design. Mechanical design aspect, design of the flange, design of the disc head, you have some other course for this. Similarly, economy, cost, they play a major role here, right? Should we take larger amount of solvent so that we have a small column, or should we have less amount of solvent and have the large column? So there is a question of economy, cost. Again, for that type of question to answer, you have a separate course in chemical engineering. Maybe at the 4th year level you have at least one course on design. So whether this is absorption, distillation, or heat transfer, we are exclusively discussing mass transfer, and in that we are trying to address certain process calculations. The amount of solvent required, say in distillation column, how many trays we need, 10, 20, 15, all right, so that air which contains 21% of oxygen and 79% of nitrogen, now we have two products. The top product contains 99% of oxygen, nitrogen, and the bottom product contains, let's say, 98% of oxygen. All right. So here our discussion is confined to height, the amount of solvent given or amount of one phase required, how much is the separations. So anything related to the separation, mass transfer, that's your orientation of this course. Mechanical design is not included here. Okay. Heat transfer, as you said, we need to have certain knowledge of heat transfer. I'm sure you have done at the second year level. Let's say Fourier first law. Okay, concept of even heat transfer coefficients. Maybe we'll have some analogy here with mass transfer coefficients, but at least that aspect we'll be addressing here. Now there is another thing here, hydrodynamics, pressure drop. So if you have packed column, how much is the pressure drop? Now, right, or if you have the fluid or water flows through these columns, will there be something called channeling? If you heard of this channeling, maldistributions. Not necessarily water will be flowing uniformly through this. If it's non-uniform, that's non-ideality. We have less separations. So again, for this course, hydrodynamics is also not included. You have done some course, at least one course, and fluid flow, at the second year or first year level, where you have addressed how much is the pressure drop. Some unit operations like absorption column will be spending at least one lecture to address issues like loading and flooding. So if you have the column, air flows from the bottom, water flows from the top, then you have that type of situations where if the water flow rate is very large, there will be entire column will be flooded with water. So certain hydrodynamics, very limited, we do have in this included in this course. Nonetheless, otherwise this course is exclusively about mass transfer. 90% we can say mass transfer. Some heat transfer, energy balance we will have in the drying, the last unit operations, or in distillation, which we will take up after absorptions. Okay, now comes the approach. All unit operations are different, yet there is one approach. If we have that type of approach, then we can learn from one unit operations and we can apply to the second unit operations. So in this course, or mass transfer separation processes, there are two approaches. One is called rate-wise approach, and the second is called equilibrium approach. So what we have in a rate-wise, we say that there is a finite rate of transfer of this component, one component, say B, from one phase to another phase. So at 1 second, 5 moles of A per meter square of interfacial area between two phases, they get transferred from one phase to second phase. So that's a rate based. Every time we are talking of rate. Second approach is equilibrium. There what do we say? Well, we have say stages, cascades, certain devices where we bring two phases in contact. Now two phases come in contact, they spend some time. During that time, yes, there is a rate, finite rate. But at the end of that stage or that time, we have two living streams which are in equilibrium. So it's an equilibrium wise approach. From one stage, now we go to the second stage. Again, bring the two components, two phases in in contact. Again, achieve this mass transfer. Then we have this equilibrium. So in the second approach, equilibrium approach, we do not have finite, or we do not have calculation at least for the rates. We work on equilibrium. We assume there is an equilibrium. So when we say the approach, now again, it's our mathematical approach. In principle, you have the unit operations like absorptions, which is carried out mostly in the packed column. Distillation, you have trace. Okay. So when you say physically trace, most likely, very often we apply this approach of equilibrium approach. Similarly, when we see some equipment where we have the two contacts, two phases in continuous contact, like in a packed column, then you will tend to apply this approach of rate. Okay. In principle, it's possible the rate-wise approach can also be applied in where we have trace, or where we have continuous packed bed, one can also apply the approach of equilibrium. So that's also possible. So what I'm trying to say here, that approach is one thing, and the real geometry, real configuration is the other thing, right? So let's make a note of these discussions here. So now we are talking of our approach to address different unit operations. Each unit operation, mind you, it's different. We need have totally different treatment, but at least we can have a common approach. So there are two approach. One is rate based. Second approach is equilibrium based. So when we say rate based, we can say N, we are talking of certain moles per second per meter square is getting transferred from one phase to another phase. So let's say this is C, component C, which is transferred from one phase to another phase. Second is the equilibrium based. Here we're not talking in terms of rate. We say that two phases, say let's say they have come in contact countercurrently, and they have reached equilibrium. So now, no matter how much time we spend together, we cannot have separations. Whatever has been achieved, that's the maximum separations. So again, talking of some example, say rate based, the most common example would be of this packed bed. So here we have packed bed, packing. We have some solids which provide very large interfacial area between two phases. We'll come back to these these aspects in details later in the class. Right now we are saying that if you look at any distance, say let's say Z, we choose del Z. Here if you look at, there is a finite rate of N at which sulfur dioxide is getting transferred from air to water phase. So this is a continuous contact. So this arrangement is continuous contact, which you can have in absorption, you can have in adsorption, mostly, right? Absorption, you can have in adsorption, you can have in drying as well. This is just an example. There you apply rate based approach. Equilibrium based approach, what do we do? Now we are talking of cascades. We are talking of stages, trays, certain devices, contactors. So we are looking at the trays like this. So liquid goes like this, vapor goes like this. If you look at one tray, there is a pool of liquid. So water, this water goes like this, air goes like this. So it makes very good contact for some time or for some very small height, in which one species has been transferred like this or this way. So here we are talking of equilibrium. The phase which is living, two streams, they are in equilibrium. You cannot have maximum transfer of whatever components you have more than what you have achieved. After this stream go to the second tray. There you have the same situations. Here you bring in contact with other liquids, they spend some time here, then they leave in equilibrium. So it's a rate wise approach. You can also think of certain vessels in which one phase is brought in contact with the second phase. So the two living streams, they are in equilibrium. They have spent some time. You bring to the second stage, stage 2, stage 1, again bring in contact with some different solvent. Again they get mixed and they leave. So notice the difference here. It's an equilibrium based approach. Here it's a rate based approach. Here we can give an example of extraction, very commonly called is followed like this. Even drying can be done like this. Adsorption can also be done by this stage wise processes. Now again we said that approach is one thing and actual geometrical configurations of the equipment is another thing, which means even if we have continuous packed bed like this, so it's a real geometrical configurations, air goes like this and water flows from this. We said that it's a continuous contact, there are no trays, there are no stages, yet it's possible that we can still apply equilibrium based approach. So this is also possible. Most commonly we apply rate based approach. Alright, so again we want to conclude here that approach is one thing and real configuration is another thing. It's a theoretical approach. How do we address how many trays are required, what is the height of the column? One can in principle can apply any of the two approaches in solving that type of questions, whether it's a continuous contact vessel or there are cascades of trays. But in general it turns out to be that if you have trays, sieves, certain containers, there you will like to apply equilibrium based approach, and if you have some continuous contact like in the packed bed column, you will like to apply rate based approach. So let's begin with this. Fundamentals of rate based approach. So we talk of rate based approach. The first thing is to discuss here is diffusion, and we say we are discussing molecular diffusion. Alright, so when we say molecular diffusion, we are saying we are not discussing, it's different from AD diffusion or diffusion in turbulent or pore diffusion or bulk diffusion. Alright, so there are different classification for this diffusion. What we are discussing here is molecular diffusion. So we are referring to movement or transport of a molecule through a medium which is could be gas or could be liquid, alright, due to certain concentration gradient del C. So for example we are talking in terms of moles per cubic meter. So a molecule is moving or getting transported because of concentration difference here, moles per cubic meter, of course by the virtue of its thermal energy. So we are saying that thermal energy is required for this movement of the molecule from one plane to another plane. That means the rate is going to descend dependent on the temperature, right? We're talking of temperature here. So we have 1 and 2. Let's look at two planes. We have the concentration here is C1 and C2. If that happens, let's say oxygen molecule, so there is a concentration gradient here, some level C1, some level C2. Because of this there will be a transfer of the molecule from one plane to the other plane. Now very commonly you have heard of this Fick's law, alright, Fick's first law maybe. So when we say application of Fick's first law, we are referring to this transport or the mode of transport, which is molecular diffusion. It is mostly, we make a note, it's prevalent in laminar flow. So let's say in a tube, if you have done hydrodynamics, we said earlier, the Reynolds number is less than 2100. It's a very slow process. So we are talking of molecular diffusion, unlike say turbulent. Okay, when we say AD diffusion, then we are talking of very large Reynolds number, in which this molecular diffusion is still prevalent, but at a is still different, but net rate of transport of this molecule is much higher in turbulent. So there is an effect of convection there, or there are ADs there. Similarly, when we talk of pore diffusion, then molecule here also gets diffused, they transfer from one plane to another plane, but by different mechanism here. The presence of wall makes a difference here. So we are talking of molecular diffusion, low Reynolds number, less than 2100, prevalent in laminar flow, driven by this concentration gradient, but it dependent upon temperature. Increase the temperature, rate will also increase. So it's most of a revision you must have done at some level here. So Fick's first law is the one which gives us at what rate molecules or moles in 1 second will diffuse from one plane to another plane. So we have this is given as minus DAB del CA over del Z. So this is a gradient. That means you have a concentration profile like this. So what is the flux here? JA moles per second per meter square. You find a gradient here at this plane. So at that plane, what is the gradient multiplied by this molecular diffusivity? All right. So just go through certain textbook or even Trebol. They have first a couple of lectures on this Fick's first law. All right. In reality, what happens when let's say we have some closed box here, and let's say we have A and B two molecules. Each molecule of A, let's say, it moves with certain velocity VA. So let's say if an observer is stationary here, he will notice that this molecule of A is moving in one direction with VA. Concentration at this location is maybe CA. Similarly, B here is, let's say, VB, concentration is CB. All right. So why these molecules move in different directions? One is, of course, thermal energy. So there is we're talking of random motion. In addition to this random motion, it's also possible that maybe there is a pressure difference, and as a consequence, this molecule can also move in some directions. So that means we are talking of a transport or flux of A moles per second per meter square having two components. One, so most fundamental would be Na moles per second per meter square is equal to VACA. So this is the velocity, this is a concentration here, meter per second, and we are talking of moles per cubic meter. So we have this flux. So at any plane, if I draw here, what is a flux? I can measure it as VACA, stationary observer. So this observer is stationary. He will measure VACA, but this will contain two quantities here. One, say the mole fraction of this species is XA at this plane. So XA into N. What is N? N is nothing but Na plus Nb. So there's one component. When entire A plus B they move along with this. They also carry this XA. Plus, said that there's another component which is Fick's first law, molecular diffusion. So this diffusion is over and above this Na. In other words, what is Ja? Flux. How will you measure this? There's nothing but Ca Va minus V. So what is V here? V is the bulk molar average velocity. So we are defining Ca Va plus Cb Vb over Ca plus Cb. So let's again try to understand this, what we are saying. What a stationary observer will observe, or measure, you will measure two quantities or two components. One by this bulk convections, we call it bulk transport, and another component is over and above this bulk transport. In other words, it's possible that Na plus Nb is 0, so there is no Xa n equal to 0, but still, because of concentration difference, by Fick's law one can measure this in Ja, which is Ca, concentration of a species at A, velocity is Va, over and above this bulk average velocity. So this Ja we can rewrite as Ca, Va minus V, which we have defined here, and this is equal to minus dAb del Ca over del Z. Why del minus sign? It signifies that the gradient is negative. Species moves or transport diffuses from high concentration level to low concentration level. So we have this negative gradient. But more important here is the definition or the fundamental understanding of this molecular diffusion from bulk transport. Alright, a species gets transported. Why? Because one is concentration difference. This can exist irrespective of whether there is a pressure drop or there is no pressure drop. So there is a concentration gradient, Fick's first law. The observer who is moving with the bulk average velocity. So all species A and B, they are moving in different directions. We can always define a quantity as if the fluid is 1. So it has a velocity V, which is dependent upon VA, VB. So if the observer moves with this V, so relative velocity is 0, he will observe certain flux, he will measure certain flux because of this concentration difference, which we call it J. So two are different. J could be 0 if there is no concentration difference. So we can have VA into Ca. That means all concentration everywhere is Ca, but there is a velocity, maybe pressure gradient, maybe because of natural convection, heat transfer difference, temperature difference. So this is the first introduction to your very basic of mass transfer. We are talking of NF flux, moles per second per meter square, which will have two components, bulk transport and this diffusion component, which is given by Fick's first law. We'll again revisit this aspect in the subsequent lecture. Thank you.